Integration with trig substitution, the infamous, uh, possibly most difficult integration technique. It's all opinion. Anyway, so trig substitution. The idea behind trig substitution is it takes what is an ugly integral or something that we can't do otherwise and makes it into something sexy. I can't believe I put that actually on here recorded for the world to see. I'm going to lose my job. Anyway, it's based on these identities. Your 1 minus sine squared equals cosine squared, tangent squared plus 1 is secant squared. And I manipulated the second one to give me secant squared minus 1 is tangent squared. All right, this is the side that we really think about. Now, obviously, we need to remember the whole identity, but that's the side that we really need to think about when we're solving these types of equations. Or not solving equations, but when we're working these antiderivatives. They are you use trig substitution when your integral contains x squared minus a squared, where a is just some number, x squared plus a squared, or a squared minus x squared. And they are almost always under a radical. That's not always the case, but usually these things would be under some kind of a square root. I should also say you use trig substitution when everything else fails. So if you try U substitution, and if you try parts, then I would dive into trig substitution. I definitely would not go into trig substitution at the very beginning. So we use trig substitution when everything, I should say everything else fails. All right, so the way trig substitution works is when you have an integral that contains something like this. Now, I'm just looking at a small piece. This is not an antiderivative, but I just want to show you how trig substitution works. So let's say I work an antiderivative and I see 1 minus x squared under a square root in that integral. Well, I start thinking, whoa, that's not what I meant to do. I start thinking about these identities. And remember, I said that we're really focused more on this side right here. We're really focused more on this side. And so what I would do is I'll look inside my integral and I see a 1 minus x squared. Well, 1 minus x squared really comes close to resembling 1 minus sine squared. So I'm looking at this. 1 minus x squared really resembles 1 minus sine squared. And in order to make that happen, all I need to do is say, let's just take out my x, and let's pretend that x is equal to sine of theta. Well, if x equals sine theta, if I make that substitution for x, then what I have under the square root is the square root of 1 minus sine squared theta. Well, 1 minus sine squared theta, now I'll use the identity. 1 minus sine squared equals cosine squared. And the square root of cosine squared is just cosine theta. So I have turned the ugly square root of 1 minus sine x squared by using the substitution. I've turned it into a cosine theta, and then we would do integration with a cosine theta in the function instead of the root of 1 minus x squared. Of course, in the end, you have to convert things back to x, and I'll show you how to do that when we actually do a calculus problem. So there's one example of how trig substitution cleans up something ugly, usually a square root. So let's look at this one, the square root of x squared plus 4. Well, x squared plus 4, that's something squared plus a number. That kind of resembles tangent squared plus 1. The only difference here is it's a plus 4, it's not a plus 1. So the way we force the plus 4 into this equation is we simply multiply the entire equation by 4, and that would give me 4 tangent squared plus 4 is equal to, okay, this must be important. Hang on. All right, I just had to pause the recording, answer my phone. I think I was trying to get an x squared plus 4, something squared plus 4, and I have that right here. Now, something to be aware of, I do have my plus 4 now. This is quantity 2 tangent theta all squared. Plus 4 equals 4 secant squared. So for number 2 right here, my substitution, I'm going to take out the x, and I'm going to plug in a 2 tangent theta. Because when I make that substitution, this turns into quantity 2 tangent theta squared, which is 4 tangent squared theta plus 4. And then based on this identity, 4 tangent squared theta plus 4 is 4 secant squared theta, and the square root of that would be 2 secant theta. So I've turned my square root of x squared plus 4 into a 2 secant theta, which hopefully is going to be friendlier when it comes time to doing antiderivatives. So that's the brains behind trig substitution. And let's try a couple of problems. Hopefully this won't take too long. These are lengthy problems, so this may end up being another 25-minute video. I'm not sure. We will see. Actually, you probably already know that because you've already looked at the time at the bottom. All right, let's see. Integration with trig substitution. Here we're actually going to do the antiderivative. So I see that 9 minus x squared, and that resembles the 1 minus sine squared. The only difference is the whole equation is multiplied by 9. So if I multiply the whole equation by 9, then I have the 9 minus x squared. So my substitution, I'm going to take out the x. I'm going to take out the x, and then I will plug in a 3 sine theta for every x, because if I do that, then this will turn into 9 minus a 9 sine squared theta. So let's do that. Let's take out the x's. So it's going to be the antiderivative. My 1 on top remains a 1. This x, we have to change this one too. We're changing all of the x's into thetas. So this turns into, let's see, 3 sine theta all squared is 9 sine squared theta. And then times the square root of 9 minus, and I'm taking out the x, and I'm plugging in a 3 sine. When you square that, you get 9 sine squared. So there's our first level of substitution. But there is one other part that I haven't tackled yet, and that is the dx. You must substitute for dx also. That is an x, and I now have thetas. So I have to find what dx is, and this is just like when we did u substitution. When we found u, we had to find du. Well, I have an x to substitute for dx. I'll simply take the derivative of what I chose for my x. So that would be 3 sine, the derivative of that is 3 cosine theta, d theta. So my dx comes out, and in the place of dx, I will put a 3 cosine theta, d theta. And now my substitution is complete, and this looks absolutely brutal. This definitely looks worse than what I started with, but it should clean up quite a bit. So let me see if I can clean that up. This is the antiderivative of, that will be 1 over, this one won't clean up, 9 sine squared theta doesn't do anything. So 9 sine squared theta square root of, now 9 minus 9 sine squared, that's this equation times 9, that cleans up to simply 9 cosine squared theta. Then I do have that 3 cosine right here, which I'm going to put that in the numerator. So that's 3 cosine theta, d theta. Now let's see, I'm going to keep cleaning that up. Antiderivative of, that's 3 cosine theta on top. The 9 sine squared is going to stay there. But the square root of 9 cosine squared would be 3 cosine theta. And this is usually going to happen with trig substitution. You usually get a lot of stuff to cancel. 3 cosine cancels 3 cosine. I'm going to go a little bit crazy. I'm going to pull this 9 out. I'm going to pull this 9 out, and that would actually become a 1/9 on the outside. And so now I have 1/9 antiderivative. The 3 cosines canceled. 1 over sine squared d theta. 1 over sine squared is, I kept the 1/9. 1 over sine squared is cosecant squared. And at that point, this thing should look very familiar, because cosecant squared is almost the derivative of cotangent. We're just missing a negative. So this antiderivative is going to be 1/9, and then the antiderivative of cosecant squared is negative cotangent theta plus a c. So there is how trig substitution cleans up an integral into something that hopefully can be done with relative ease. Now, the final problem we have is we have to substitute and get our original equation, or get our answer in terms of x, because that's what we started with. The theta was just kind of an in-between to get to an integral that we could work out. And so now I have this answer, a temporary answer of this, and I've got to get it back into terms of x. And this is the step that, for some reason, what I've done so far doesn't make you angry, but this next step does. And I don't know why. I guess it's just because you're weird, because I'm definitely not weird. I'm anything but weird. Um, anyway, this is my equation that ties x to theta. And so what I could do, if I wanted to solve for theta, I could say x over 3 is equal to the sine of theta. And some of y'all may be thinking, oh, well, then that means theta is equal to the inverse sine of x over 3. Or you could say arc sine x over 3. If theta is the inverse sine of x over 3, then we could just plug in inverse sine x over 3, and we get an answer of, let's see, I'm going to go crazy and call that negative 1/9. That would be the cotangent of the inverse sine of x over 3 plus c. All right, now that does give me an answer in terms of x. Technically, that's okay. If we were working a free response question and it was not multiple choice, I would be okay with that answer. However, if you punch this integral into the calculator, let me show you what you will get. There we go. So I punched it in my calculator, and you can see right here, when I do the antiderivative of our original function, it tells me the answer is negative root 9 minus x squared over 9x. It doesn't give me all this stuff. You need to know how the calculator came up with this solution. And the way we do that is we actually ignore this inverse sine stuff. While it's true, this is not going to help us. I'm going to take this right here. I'm going to take the x over 3 equals sine theta, and I'm going to go back and channel my geometry skills. Y'all remember geometry? 9th grade for most of you. And I remember that sine theta, sine of an angle, is opposite over hypotenuse. Remember SOHCAHTOA? So sine theta is opposite over hypotenuse. So what I do is I draw a triangle. I draw a right triangle. I pick some angle to be theta. And I know that if sine theta is x over 3, I know the opposite is x. My hypotenuse is 3. And if I do the Pythagorean Theorem, you get the square root of 9 minus x squared for this side length. If you don't believe me, this side length, let's see, that would be a. So a squared plus x squared is equal to 3 squared. A squared equals 9 minus x squared, and voila, a is equal to the square root of 9 minus x squared. So I would take that out, and I know that this side length is the root of 9 minus x squared. Now I go back to my answer, and my answer says the negative cotangent, the cotangent of theta. Well, cotangent, I'm thinking, let's see, cotangent is the reciprocal of tangent. So cotangent is going to be adjacent over opposite. Well, if I look at my triangle, here's my angle. The adjacent side is, let me see, so it's negative. The adjacent side is the root of 9 minus x squared. The opposite side is just x. And I'm multiplying that by 1/9 plus some c. And that is what we have here. Negative root 9 minus x squared over 9x. The calculator doesn't do the plus c. I don't know why. It actually has the ability, but it doesn't do that. And that is how we will answer our questions when we do trig substitution. You have to go back and draw the triangle to get my cotangent theta back into terms of x. So there is example number 1. Let's see, so 15 minutes. Maybe I can knock out the next problem in 1 minute. That was stupid. 10 minutes. All right, looking at this problem, notice there's no square root. Oh, geez, that's not what I want. Notice there's no square root in this problem. However, when I try u substitution or parts or anything else, this thing fails. So I'm going to think about which trig identity this looks like, and 1 plus x squared looks a lot like 1 plus tangent squared of an angle equals secant squared. So I see a very strong resemblance there. So I'm going to take out my x, and I'm going to plug tangent theta in its place. Because if I do that, 1 plus tangent squared becomes secant squared. But remember, you have to substitute the dx. That is the biggest mistake people make with trig substitution. You have to do dx as well. The derivative of tangent is secant squared theta. And so I will do my substitution here. So this turns into, oh, that was a horrible integral sign. That's still not much better. 1 over 1 plus tangent squared theta all squared. And then my dx, don't forget, you have to do the dx as well. Dx is secant squared theta d theta. So let's see. So now we start cleaning that up. Let's see. 1 plus tangent squared is secant squared. So I have secant squared theta squared. My top is secant squared theta d theta. And this does a lot of cleaning up. I'm going to work to the right here. So let's see. I have a secant squared on bottom and secant squared on, or a secant squared on top and secant squared on bottom. This secant squared is going to cancel one of the secant squareds here, leave me with the integral of 1 over secant squared theta d theta, which turns into the antiderivative of cosine squared theta. Right? Now, the antiderivative of cosine squared is one that we have talked about. The way you integrate cosine squared is you do, oh geez, my integral signs are brutal today, is you turn cosine squared into 1 plus cosine of 2 theta over all over 2. So cosine squared is equal to 1 plus cosine 2 theta all over 2. So let's do that. That's going to turn into 1 plus cosine 2 theta all over 2. I'm going to do two things at once. No, I'm not. I'm going to pull the 1/2 out. I'm dividing by 2, so I'm going to turn this into, geez. There. 1/2 the antiderivative of 1 plus cosine 2 theta d theta. And then finally, I can do the antiderivative. That is 1/2 of the antiderivative of 1 is theta plus cosine 2 theta, the integral antiderivative of that is sine of 2 theta divided by 2. Okay, so we've done what I consider to be the hard part. I have done the antiderivative. Now we have to get things back into terms of x using this identity, or this, not identity, but this substitution right here. X equals tangent theta. If x is equal to tangent theta, now remember tangent, if we think about our triangle, tangent, I'm going to write it as a fraction, as x over 1 would be opposite over adjacent. So I'm going to draw my triangle. Right triangle, I pick some angle theta. Tangent is opposite over adjacent. I'll do the Pythagorean theorem to get this side, so x squared plus 1 squared is my hypotenuse squared, and you get the square root of x squared plus 1. Nice little hiccup there. And if you've paid attention, this one's going to be a little bit different, but usually for your third side length, you get the same thing that was in the original problem. Now, we don't have a radical in the problem, but we do have 1 plus x squared, and that's what we got when we solved our triangle. On the very first problem, our original problem had the root of the root of 9 minus x squared, and when I solved for the missing side length, I got the root of 9 minus x squared. That should happen. So it's kind of a way you can kind of check to see if you've done things correctly, a small way of checking. All right, so now I have my triangle. The problem here is this is sine of 2 theta, not sine of 1 theta. And my triangle has 1 theta in it. So I've got to undo this triangle somehow. Let's see, I'm not undo the triangle. The sine of 2 theta. There is an identity for sine of 2 theta. that says sine 2 theta is actually equal to 2 sine theta cosine theta. And if I use that identity, now I can actually look at this triangle. So I'm changing this to 1/2 theta plus 2 sine theta. Ooh, look at this. The 2's cancel, don't they? 2 and 2 cancel. So that would just leave me with sine theta cosine theta plus some constant. And then finally, let's see, I think I can finally work this out. Sine theta is opposite over hypotenuse. So the opposite is x. The hypotenuse is root x squared plus 1 times cosine theta is adjacent over hypotenuse. The adjacent is 1 over hypotenuse root x squared plus 1. So I plug that in for cosine theta. I still need to substitute something in for the theta. In this case, the triangle isn't going to help. And I actually will use inverse tangent this time. If tangent theta is equal to x, then that means theta is equal to the inverse tangent of x. So I'll take out the theta and I'll plug in inverse tangent of x. And then all of that is times 1/2 plus some c. And finally we finish. Finally we finish. Undoing your thetas and getting them back into x is almost as big a problem as the integral itself. So there we go. That's the idea behind trig substitution. They are extremely lengthy problems. I'm actually very proud of myself that I was able to answer both of these using only one slide per page. So that was 2 problems of trig substitution, and we'll hammer this out in a little more detail later.